Hi all, today we'll discuss the last theorem of section, that is the theorem 3.6, in which we will discuss the uh, average order of the divisor function. As it is in the last case, we have discussed uh, the divisor function for negative positive values of alpha and 0. Now we will discuss in this theorem the average out of the divisor function for negative values of alpha. So if we pick a positive quantity beta greater than 0, then we will discuss the average order of sigma minus beta of n. We will discuss this theorem in two cases. In case 1, we will discuss it for beta is equal to 1, and in the other case beta not equal to 1. Okay, let's see the theorem and followed by its proof. Theorem 3.6. This theorem states that if beta greater than 0, we let delta is the maximum of 0 and 1 minus beta, then for x greater than 1, we have summation n less than or equal to x sigma minus beta of n equal to, we have two answers. One is for beta not equal to 1, and next is for beta equal to 1. In this case, we get the value theta of for beta not equal to 1, we will get the answer theta of beta plus 1 times x plus O of x raised to delta. The other case, we will get theta of 2 times x plus O of log x. Okay, now we begin the proof. We start with LHS, sigma n less than or equal to x sigma minus beta of n, and this is equal to sigma n d less than or equal to x sigma q less than or equal to x by d 1 by d raised to beta. You can replace this d by q, both are the same answer because these pairs are symmetric. We have already discussed all these things in the previous two theorems, so we are not going to explain again this equality. So this will give summation d less than or equal to x 1 by d raised to beta summation q less than or equal to x by d 1. Okay, that is equal to sigma d less than or equal to x 1 by d raised to beta times, using the asymptotic formula, we will get this is equal to uh, x by d plus O of 1. This is the d part of the asymptotic formula. So this will be equal to sigma d less than or equal to x by d raised to beta plus 1 plus sigma d less than or equal to x of 1 by d raised to beta. And you can rewrite this as, from the first summation we can take x out, then the remaining will be the summation d less than or equal to x 1 by d raised to beta plus 1, and from the right O can be taken out, so this is O of summation d less than or equal to x 1 by d raised to beta. Okay, now we set uh, case 1 as beta not equal to 1. That implies beta is not equal to 1. The LHS will from the previous expression can be written as, so this is nothing but sigma n less than or equal to x sigma minus beta of n equal to, we can rewrite this as x times, using again the asymptotic formula. So this will be x raised to minus beta divided by minus beta plus theta of beta plus 1 plus O of x raised to minus beta minus 1. So this will be the sum written here, plus the second term will be O of, if you use the asymptotic formula again for this term, you will get this will be x raised to minus beta plus 1 divided by minus beta plus 1. We have the assumption that this beta is not equal to 1, so this now be 0, so this a finite value plus seat of my beta plus O of x raised to minus beta. This is the this is the second term. This is the second term here. Okay, now look at this term. We can say that if we know that minus beta is always less than minus beta plus 1. So among these three terms, this will dominate among. So we can neglect this term. And if we consider these first two terms, if 1 minus beta, this is actually a function of order 1 or x raised to 0 of x raised to 0 is, this can be considered as of x raised to 0. So among these two terms, if 1 minus beta is less than 0, then x raised to 0 dominates. Otherwise this 1 minus beta dominates. That means if we set delta as the maximum 1 minus beta and 0, we can say that that maximum value dominates among these two. Okay, so we can take it as O of x raised to delta if delta is the maximum of 1 minus beta comma 0. Okay, and this will be equal to this is nothing but x raised to minus beta, x into x raised to minus beta is x raised to 1 minus beta divided by minus beta, and second term will be seat of beta plus 1 times x plus the third term will be x times of this, that is O of x into this term. So we can cancel one x from this, then this will be O of x raised to minus theta minus beta. Then again consider all these. This is a function of order x raised to 1 minus beta, and this is x raised to 1, and this is O of x raised to minus beta. So among these three, if we leave this term, among these two we can say that these two terms constitute O of x raised to delta, where delta is the maximum of this 1 minus beta and 0. So among this we can say that O of x raised to delta will dominate. Okay, so this can be written as x raised to this will be, this can be written as theta of beta plus 1 into x plus O. Okay, in the case when beta equal to 1, this term, this is exactly same as this one. So this will reduces to x times theta of 2, and the other terms, what happens to these terms? That is O of sigma d less than or equal to x 1 by d raised to beta, and this is equal to O of if beta is equal to 1, that will be equal to summation d less than or equal to x 1 by d, and this is equal to o of, this is equal to log x plus c plus o of 1 by x, and among these three terms all log x will dominate, so this will be equal to o of log x. So the second term can be reduced to o of log x, and first term can be reduced to from this you can write theta 2 into x. Okay, so in the case when beta is equal to 1, we have the partial sum is equal to uh, theta of 2 times x plus o of log x. Okay, so this is the two cases what you have to prove.